Welcome to the fifth video of a 5-video series on linear regression, hypothesis testing. Suppose we were to claim that there's a correlation between the number of years attending college and income. Sounds logical. And suppose we wanted to test this claim with a significance of 5%. What does that mean? Well, with any claim, there's always a likelihood of a false positive. You claim that there is a correlation between two variables. You find a correlation between two variables when there actually isn't one, just because of some random set of data that led you to that false conclusion. So this false positive, or what statisticians call a type 1 error, doesn't happen too often, but it can happen. And when we say we're going to test a claim with a significance of 5%, that means if, at the end of the process, we decide that there is a less than 5% chance that our conclusion, which supported the claim, has less than a 5% chance of being a type 1 error or false positive, we will then accept the claim as stated. So here's some data. Here we see individuals who have reported their amount of schooling and their annual income. It's a small sample meant to represent a large population, and we're trying to prove this claim for the population, not the sample. So the hypothesis testing process, as you may recall if you've seen prior videos of mine on this topic, is a 5-step process. But as a student, we sort of pick it up in the beginning with step 3, because the claim and the stated significance and the gathered data are typically done for us by the professor or textbook or whatever it is we're working in. Although it is possible for students to go out and gather their own data, the typical scenario is that you've been given the sample data and you're going to start with what in the real world will be step 3, and we're going to assume that there's no correlation. Why would we want to assume there's no correlation when we started this process trying to show that there was in fact a correlation between number of years in college and income? Well, this is how hypothesis testing works in general. We want to prove something, and so we assume to the contrary that there's nothing there that supports our proof. And what we can do is look at this data in the light of that assumption, and we may come to a conclusion that if this assumption were true, that there is no correlation, that the data that you see here would be very unlikely to have been produced as a random sample, in which case we can accept the claim and that there is significant evidence to support it. This assumption that there is no correlation is called the null hypothesis, and the claim that we're making is the alternative hypothesis, which we will adopt if there's evidence to overturn the null hypothesis. We'll see how all that plays out. The next thing that we want to do is find the probability that under the null hypothesis, under this assumption that there is no correlation between these variables, we want to find the probability that this data, this random sample, could have occurred just coincidentally. Here's a scatter plot of the data, and you can see a slight upward trend. There is sort of the general notion from the scatter plot that the more years of college you attend, the more money you make, as a general statement. So, what we'll do to find this probability is we'll look at our claim about the correlation. We'll use a test statistic, and we're going to use the t-distribution. And it turns out that we can convert the correlation coefficient, which you've heard about in previous videos, the so-called R, we can convert that based on the sample size into a t-score and use the t-distribution and the t-cumulative distribution function in order to compute the probability that such a sample would have been produced under the null hypothesis, meaning that such a sample would have been produced if there actually were no correlation between schooling and income. By the way, you may recall DF as being degrees of freedom from previous videos. And the degrees of freedom, you might remember that always being n-1 or 1 less than the sample size. In claims about a correlation, it's n-2, and this 2 essentially is because we have two variables, the schooling and the income. So what we can do is plug all this data into a calculator, and we'll get the linear regression screen that you see here. It has a lot of information in it, but what we care most about is the R value, or the so-called correlation coefficient. Because that correlation coefficient, along with the sample size of 15, can be plugged into our t-test statistic. And in this case, the calculator will show that t is about 1.962. Okay. Now, plugging that into our cumulative distribution function for the t-distribution will give us a probability that the correlation coefficient is 0.478 or higher. And the calculator will show that that probability works out to about 3.5%. Now, what does this 3.5% roughly mean? It means if the null hypothesis is true, if there is in fact no correlation between these variables whatsoever, there's only a 3.5% chance that the correlation coefficient could have been 0.478 or higher with this sample size. What I'm going to do is I'm going to double that. Why? Because while there's a 3.5% chance the correlation coefficient could have been 0.478 or higher, there's an equal, by symmetry, an equal chance that it could have been negative 0.478 or lower. And since the claim, notice at the top of the screen, since the claim did not make any assertions that there was either a positive or a negative correlation, and simply generalized that there is a correlation between these two variables, then you have to take both of these 3.5% probabilities into account, double that, and get approximately 7% as the probability of a type 1 error. Now, this logic is very strange and sounds foreign to most people. If you're a student in a statistics class, you can make it simple on yourself by simply asking, did the claim state that there's a positive correlation? Did the claim state that there's a negative correlation? Because if it stated neither, which is often the case, and it is the case here, then you can assume that they're claiming that it could be either way, and just multiply the probability value by 2 to get your final probability of a false positive. Now, the question now is, should we reject the null hypothesis? Is there enough evidence to say that the null hypothesis is probably false and thereby accept the alternative hypothesis? Well, in this case, no. To state our conclusion, which is our next and final step, we consider the fact that the claim was made with a 5% significance, but we ended up with a slightly over 7% chance of a false positive or type 1 error. And since 7% is greater than 5%, there is not sufficient evidence to support the claim that there is a correlation between these variables. Now, it's worth noting that just because we don't have enough evidence to support the claim doesn't make the claim wrong. Is there a correlation? Is there actually one between schooling and income? My intuitive guess is yes. And the fact that we got a 7% chance of type 1 error indicates that there is a reasonable assertion to be made here that there is some correlation, but since we set out to prove it with a 5% significance and we set the bar that high, we did not achieve that. Therefore, we're not saying the claim is false, but we're saying we don't have the evidence with this particular data to support it. Here's a second of 3 examples. Claim: there's a correlation between baby age and baby weight. Well, before we do any statistics here, this seems almost common sense. Of course, there's a correlation between the weight of babies and their age. But let's look at it more statistically. We're going to test this claim with a 1% significance. We're setting the bar higher than in the last problem. Here's the data that we collected. This shows babies. Each line represents a baby. Their age is in months and their weight is in pounds. So we're already at step 3 of the hypothesis testing process. And again, as a statistics student, when you're given a problem on a homework or test or wherever you happen to be doing it, you're really jumping right into step 3 because, as I said before, the claim and significance have been stated by the professor or textbook. The data has probably been already gathered, and you're just taking off with the statistics portion of the math. So, first thing we do is assume there's no correlation. Now, this is counterintuitive. In the back of my mind, I'm thinking, of course there's a correlation between baby's age and baby weight. But we're going to assume to the contrary, that there is no correlation. Our so-called null hypothesis might be useful in actually proving the opposite of what we're assuming here, which is the alternative hypothesis. So, same game plan as last time. We're going to find the probability under the assumption of the null hypothesis that the data could have been as linear as it appears to be in this scatter plot. Now, it's clearly not perfectly linear, but you can see by the way these marks are distributed in the graph that as age increases, weight seems to increase. So there, as intuition would guide, there is or appears to be a positive correlation between age and weight for babies. So we'll do the same as before. We'll use all the statistical tools that we have to test this claim using the t-distribution. But in order to do that, again, we need the correlation coefficient for this particular sample. Well, typing in the two lists of age and weight into your calculator, or whatever software you happen to be using, should give you a correlation coefficient of 0.717, which is pretty close to 1, which is the highest a correlation coefficient can be. So already it looks good to assert that there is a correlation between age and weight, as we suspect. Plugging in the R value, and notice also plugging in 17 for N, because there were 17 babies in this sample, calculator gives me a relatively high t value, which I can then plug into the cumulative distribution function for t and get a very low probability that the correlation coefficient would be this high. So what does this 0.000604 represent? It represents the following. The probability that if the null hypothesis were true, if there were no correlation between these variables at all, the probability that 17 random samples could line up as linearly as these samples did is that 0.0006. In other words, it's very unlikely for data to line up like this when there's no correlation at all. Now, not that it's going to matter, but I'm going to double that for the reasons discussed on the previous problem. And to keep it simple, look back at the claim at the top of the page. There's no assertion of positive or negative correlation, so we have to assume they're just talking about a correlation in general, meaning it could be either, therefore we double the value. So this null hypothesis is very unlikely to be true because there is such a low probability that the data would have lined up this way if it were. So when we state our conclusion, we recall that we're testing this claim with a significance of 1%, and the probability value that we got is way lower than that. Notice it's about 1/10 of 1%, and that indicates that there definitely is sufficient evidence to support the claim. Here's our last example. Suppose there's a claim that there's a correlation between intelligence quotient and your daily sodium intake. We want to test this claim with a 20% significance, setting the bar real low. Here's the collected data. It shows different people, each with an IQ ranging from 85 to 115, and it shows their sodium intake in milligrams per day. Okay, So again, we're already on the third step of the hypothesis testing process once we get our data given to us, which as a statistics student is handed to you in the problem. And we're going to start as usual by assuming there's no correlation, which is contrary to what it is that we want to show. That assumption is called our null hypothesis, and we want to use it as a mechanism to accept the alternative hypothesis if the data in this table that we've collected is strong enough to show that. Same plan as before, we're going to find the probability that the data could have been as linear as it is by accident, if there were in fact no correlation. Now you'll notice by looking at the scatter plot, the data is not particularly linear. And so just on a pure intuitive level, the visual fact that there doesn't appear to be significant correlation here is already leaning me towards the notion that there is not sufficient evidence to support this claim. And just as a side note, why would there be any correlation between IQ and sodium intake? Maybe there is. Moving on. So we'll do our usual. We'll use the formulas and the t-distribution to find the probability of a type 1 error. So this information here, this correlation coefficient of negative 0.201, that came from, as usual, typing the two lists into a calculator or other software that will feed us the correlation coefficient. And I can take that along with a sample size of 12, you'll notice, the number of people who we gave the IQ test to compute t, and we can plug that t into our cumulative distribution function to get a probability value. Now what does this probability value mean? It means that the probability that the correlation coefficient was negative 0.201 or lower is 26.5%, assuming the null hypothesis is true. So doubling that as we do gives us about 53% probability of a type 1 error. Now remember, you would always double the probability if the claim made no assertions about a positive or a negative correlation, which it didn't. If the claim specifically said positive correlation or negative correlation, we wouldn't double the probability value. So what this means is, if the null hypothesis is true, there's a 53% chance the data could have looked like this. So that's not overwhelming evidence to overturn the null hypothesis. And therefore, and when I state my conclusion, given the fact that I wanted to test my claim at a 20% significance, and 53% is much higher than 20, then there is in no way sufficient evidence to support this seemingly ridiculous claim that there's a correlation between IQ and sodium intake. And with that third example, that concludes this fifth video and this series on linear regression.